Swayam Prabha. Digital India. Educated India.
So if you substitute back these things over here, if you put V equals to 10, I equals to 179.7 and Q equals to 3.5 times S, what you will eventually get that your Q in the flange becomes 35S divided by I. So also, so you see that one thing that here, that it is a linear variation, right? So it is at S equals to 0, at this particular point it is going to be 0, it is going to be maximum because we are dealing with the flange. The maximum extent the flange goes is up to this half of this 5, that is at 2.5 over here. So let's try to calculate at 2.5 what happens. So this essentially your indicates overall that your Q of F is 0 at S equals to 0 and Q of F is maximum at S equals to 2.5 inch. So if you calculate at 2.5 inch, what you will get this at 2.5 inch, it becomes a Q of F is 35 times 2.5 divided by your 179.7. Right? Now if you put all those values over here, you will get the Q of F, as I have this calculated already, it is going to be 0.48. Remember the unit of Q is force per unit length, so it is going to be pound per inch. Right? So you're having a linear variation from this point over here up to this one. So let's maybe go ahead and sort of try to mark that one. So if I try to mark over here, it is going to be somewhat like this. This should be ideally at the center line, but you get the idea. So here the value of this thing is 0.48. Now what did we sort of hypothesize from here, that this Q must be equals to this Q because the water has to flow out over here. So let's try to calculate for the web now, since this is the web that you see, right? So for the web, let's try to calculate over here and let's see if we get the exact value of 0.48 or not. Now for when you are trying to calculate for the web, that is you are trying to calculate the Q maybe at this particular point over here, Q web, at that interface that you see, right? So if you try to calculate over there, then the area that you have to consider is this entire area, the area that you have left behind. So let's calculate for the web. Let's write it for the web. QW at interface is going to be equals to same formula, VQ divided by I. Now in this case, the Q is going to be what? The Q is going to be have this 2.5 over here, slightly more than 2.5, but center line dimension suffices. 2.5 times this thickness, so that is 1 inch over here. So and times the distance to the neutral axis, that is 3.5. So here in this particular case, you get the Q as 2.5 times 1 times the distance, that is 3.5. Right? So you see, if you put this back over here, right, everything, and if you put V equals to 10, what? So your V is equals to 10 and your I is 179.7, right? Inch raised to 4, and you see if you plug all this in, it eventually becomes the same thing that you had calculated over here. See, 10 times 3.5, 35 times 2.5 divided by this. So here also what you will get is that here also you will eventually get a 0.48. It's the same, it's like the flow of water, whatever water goes there must come out of the other side. So here also if I have to draw in this particular place, so here also what I get is essentially the same ordinate of sorry, this became a little longer than I intended to, so let me redraw that. Right. So here also you get the same ordinate as 0.48. Now what we know, that in this web, this vertical face, it is going to have a the minimum value over here and parabolic variation, and the maximum is going to be here. So I need to calculate at this point as well. This point is this D point which was there. So at this particular point, so let me maybe mark that point also just to have a reference. So this is the D point that we had over here. So let's calculate at D and let's see what we get at that particular point D. So at D. Now for D, remember, since you are here, you are trying to calculate that what is the Q wave at this particular point. So at this particular point, since you're trying to calculate here, the area you have left behind is essentially this area. You started from here and you're doing say 1/4 of this one, so you have to take this particular area that is there. So if you calculate that one, so essentially this area, so that can be broken up into two chunks. So for calculating that capital Q, so for this one, when you calculate the capital Q, you have to break the area into two chunks. So this one, a prime y bar prime for this one, a prime y bar prime for this one. So I will just write it out quickly, you can go back later and verify. So this boils down to this is for the first chunk, this is for the first area, this is the top one. So 2.5, this distance 2.5 times 1, and the distance from the centroid here to the neutral axis, this is 3.5. and the second one is for this chunk over here, that is 3.5 times this thickness is 1 inch throughout, times 1 times the the distance to the neutral axis. So that should be 3.5 divided by 2, sorry about that. Right, so if you add that up, you will get it as 8.75. Now again the same thing, if you calculate VQ by I, so at D you are calculating, so you will get a value of 0.83 kilopounds per inch. Sorry, in the previous ones I wrote the dimensions as wrong, so it should be kilopounds because your force is in kips, right? I mistakenly wrote that as just the pounds. Kips is kilopounds, so it will be kips, so all throughout it's kips. So again, so what we see over here, that at this particular point you're having a value of 0.83 and the variation from here to here is going to be parabolic. So let's just draw that. First the value and then the parabolic variation we'll draw. So here you have 0.83 and the variation from 0.48 to here is parabolic. So this is just for 1/4, the remaining it is going to be the same. So I will quickly draw for the remaining, you can come back and check that. So this is the overall stress distribution, sorry, the shear flow distribution, not the stress distribution. As you can see, this was the half, this we drew over here, 0.48, 0.48, and at the center 0.83, and it is repeated across all the 4 quadrants that you have in your diagram over here. So just to note, remember that this is the linear variation that you were having and this is the parabolic variation. So I hope this overall example was clear. Now although this one is gives you the distribution of Q, you can imagine that the distribution of your tau, the shear stress, it is also the same. Why? Because your Q equals to tau times T, so tau equals to Q divided by T. So if you take each of these values and you divide by the thickness, which is the same, in this case the thickness is 1 inch throughout, so if you divide it by the thickness, you will get the same the same profile for the shear stress distribution. So I hope this overall problem was clear and that you're clear with the concepts of shear flow distribution in thin wall section. So we have reached the last topic on our chapter on shear, and this topic deals with shear center, which is particularly valid for thin wall sections. So until now we have seen in the last topic the shear flow in thin wall sections, and now we will see that what is a shear center and why is it important for thin wall sections. Now to understand the concept of shear center, first let us look at certain sections. For example, if you look at sections where which have 2 axes of symmetry and the principal centroidal axis coincides with the axis of symmetry. This is the I section which we had seen for the thin wall section. This is not a thin wall section, this is a solid rectangle that we have over here. But you see in both of these cases, both this one and this one, it's a doubly symmetric sections, so it is symmetric about the vertical axis, symmetric about the horizontal axis over here. Same for this one over here. Now, so these are the axis of symmetry, and the your centroid is exactly at the center, and it splits the whole beam, right, into axis of symmetry about the vertical as well as the horizontal axis. Now, for these sections, when you are applying a load, right, so if you have these sections, when you're applying a load at the centroid, so exactly at the centroid you're applying a load. Say this beam is fixed at this end over here, is a cantilever beam. When you are applying a load P at the center, you will see that these kinds of beams, both this one and this one, if you have I section also, it bends and there is no twisting, right? So for example, like these beams do not undergo this warping kind of a thing, this twisting, this torsion, internal torsion doesn't occur, and this is also pretty intuitive to understand. But unlike these beams which have two axes of symmetry over here, if I give you a beam which is something like this, right, and this need not be thin wall, this can be any kind of a channel section. This is called a channel section because it looks like this C over here, so it is called a channel. So for this channel section, so this is a channel which is turned upside down over here. Now for this one over here, so it has one axis of symmetry, whereas if you turn this one over here, it is symmetric about this axis, right? So it is also has one axis of symmetry about here, but about this particular axis, about the vertical axis, it is not a symmetric section, because if you see about the vertical axis, on the left hand side you have this part, and on the right side you have this part, so it is not a doubly symmetric section as you have. Now for these beams, if you apply the load for about the centroid, so let's take a look at for this one over here, for this section. Now if for this section, if you apply a vertical load passing through the centroid, you will again have the case where there is only bending and no torsion. So let's take a look. So if you have something like this, the line of action of P, it's a cantilever beam. If you put a load through here, you see this has already bent, so it has only bending, but there is no twisting or no torsion. On the other hand, on the contrary, for this one, and this is also takes a bit of your imagination, and you can maybe do this experiment at home as well, like these channel sections. You may not have a steel channel section, but the electrical wires in your house which passes through the through the wall, and to conceal them you put these these kind of channel sections that you have made of plastic, right? So if you happen to have some at your home, you can try it out, that if you keep the beam like this and if you apply the load, can you sort of intuitively imagine what is going to happen? It is going to bend for sure, but it is also going to have some amount of twisting, some amount of torsion. So let's take a look. So if you have something like this where the load is again acting through the centroid, and you can intuitively imagine that along with bending, it is going to have some amount of twisting as well, right? So this is an experiment which is done on the lab, and that's why I've written based on true story. So you see here, this channel section that you have, it was fixed at the one end over here, and this load, this line of action of the load, it passes through the centroid. So this C over here, if you see, the originally the line of action passes through the centroid. Now when this guy has bent, along with the bending, it has had certain amount of twisting also. You will do this experiment in your solid mechanics lab as well. There you can see that this kind of phenomena exists. It is valid. Now the question is that why does it happen? Why, when for sections which have only one principal axis of symmetry and not the other axis of symmetry, when we apply the load over here, why along with bending do we also have torsion? So let's go ahead and take a look. And why is it important? Because if this section is thin walled, right, it undergoes significant amount of torsion, and thin walled sections are essentially very weak in torsion. That's why we need to take into account or learn about this concept of shear center when we talk about thin walled sections which have only one axis of symmetry. Now let's see why it happens. Now this is again the similar kind of a beam over here which I have taken, where the load is applied through the centroid. Now if you take an internal section, right, if you take that internal section over here, this is the resisting force that you are having. This resisting force equals to P, and then because of the shear flow, remember we have considered the shear flow over here, because of the shear flow you are going to have these horizontal loads which are acting on the top flange and the bottom flange over here. Remember, here again the top is the flange, the bottom is the flange, and the middle portion is the web over here. Now I hope you are clear with this direction of the forces. This is essentially like if you are say taking a beam. Let me turn on my pen so that I can show you. So suppose if you are taking a cantilever beam for that matter, right, what you have over here, and if you're applying the load, say a load P which is acting, if you take a section somewhere and you're only taking the right hand half, only this part over here, what you essentially see is that you have this load P, right, and you will have this V and the moment and so on. So I'm not drawing the moment. So this is the V equals to P that you are having, which is essentially this guy, this vertically acting load over here. So you're looking at an internal section over here, right? Now along with this, you will, because of the shear flow, remember that we had seen for the thin wall eye sections that it is like the flow of water. So here at this interface, you are having this vertically acting V over here. So according to the direction of the flow of water, the water must come through here, it must go through up, and it must exit over here. So you are going to have some amount of shear flow is over here in the horizontal planes over here. Okay, now if we take a look at this one, just this small section that we are looking at, if we take a look at this one, this is how the flow of shear happens. Now remember, here again, your vertical acting upwards force in this section, if you look at the section overall, if you look at a complete zoomed out view, you have this vertically acting force V, which is equals to P in this particular case, and that gives rise to this shear flow over here. Now this is again like the flow of water, you are having a vertically upwards acting force, so that leads to the flow of water. It must start from here and it is 0 over here. Remember at the edges, remember what we had discussed, that at this edge over here as well as this edge, the magnitude of the shear flow or the shear stress tau, right, because they are correlated, must be equals to 0, because on the plane which is going into this slide over here, you do not have any externally acting shear, so the complementary shear must also be 0, whereas internally you must have a substantial amount of shear flow or the shear stress over here. Also remember, since it's the flow of water, this vertical arrow that you see over here must be equals to this arrow over here. Now last thing to remember from what we had seen before, that if the line of action of the force, this V, is acting vertically up over here, for what we had learned from our previous discussion on shear flow, is that for sections of the member which are perpendicular to the line of action of the force, this the shear flow is also perpendicular, it acts parallel to the edges, and in the in this vertical section, which is parallel to the line of action of the force, the shear flow is going to be parallel, right? So if we now draw the magnitudes as we had done in the previous example, you are going to have a linear variation. Remember, in the horizontal members, that is the members which are perpendicular to the line of action of the shear, the flow, the nature of the shear flow or the shear stress is linearly varying. So it is going to vary from 0 over here to a maximum value over here. Then in this section, the variation is going to be parabolic, and then again it is going to be linear. So it is look something like this over here, and you can easily derive this one. For example, how will we get this tau f over here? We take a small section, we have done this already. We'll take a small section, you find the q of that section, from the q you can get the tau. Now remember that this, what you're looking at, is a shear stress, or if you the diagram for the q is also going to be the same. It is just will be this tau f times the t, the thickness, which we have looked at, right? So here this is the shear stress. So now from the stress, if I try to get the force, how do I get the force from the stress? So here the force from the stress would be simply, so this is the triangular. So remember, we always try to idealize, and remember one more important thing, these triangles and this parabolic part, it is only a representation of the magnitude, not the direction. The direction of the shear flow, the shear stress, happens something like this over here. Now from the tau f, now from this stress diagram, if I try to get the force diagram, so this is how it looks like over here. Now a quick question, how do I get this ff over here? It is simple. This ff you can simply get, see, the stress varies from 0 over here to maybe a highest magnitude, something over here. So it is going to be half times the length of this one times the height of this one. So that will give you the dimension of the length 2 times if you multiply the value of the peak stress over here, you will get this ff. We'll do a problem example there. You can see that how we get this from the shear stress distribution. How can you get the forces? So anyway, the in a nutshell, what I'm trying to say is that here, because of this, tau f, you are getting a total. So this is the total force, because the force is just, one quantity. It is not, varying from small to large. This is the total resultant force which is acting on, this horizontal face. And as you can say that this ff and this ff is going to be the same, because about this horizontal axis is symmetric, so it is going to be ff and ff is going to be same. And this one must be equal to P, because externally you are applying P. So to obtain the vertical force equilibrium, see, these horizontal forces are automatically balanced, because this is equal in magnitude and opposite in direction to this one, so that is balanced. And this P must be equals to this externally applied P over here. Now very important, now you have to closely observe over here. See here, these two are equal and opposite forces which are separated by a distance h over here. And also, if you look at this structure, if you look at this entire section, the section which you've cut over here, essentially from here to here, if you look at this entire section, the line of action of the P at this end is at the center. So if I have to sort of quickly mark that, so this is my line of action of the externally applied P which is acting on that section. Now because of that P itself, internally you're having that V which is equals to P over here. Now take a look at these forces. This ff and this ff are equal and opposite forces separated by a distance h. Similarly, this P and this P are equal and opposite forces separated by some distance wherever the centroid is. Now can you now understand that why along with bending you're also having a certain amount of twisting? Yes, you're right. You see this ff and this ff over here, this force and this force forms a couple, a positive couple. So it forms a couple like this over here, right? Similarly, this force and this force equal and opposite separated by a distance, that also forms a couple over here, right? So as a result of this overall couple, you are getting that amount of twisting that you are having. So if we just go back to the previous slide, right, so this is the twisting because of these internal forces developing at the section. See, this is also twisting in a clockwise manner, exactly what we saw over here, exactly what we saw. This kind of twisting happens in a clockwise manner. That's why you have a twisting kind of a phenomenon. Now, so the question here is that how do we sort of resist this twisting kind of a motion that is there? How do we resist this twisting? So as a result of this twisting, we saw that you're having the twisting in the beam over here. Now you see what is there in our hand. What is there in our hand in terms of this beam? We cannot do anything with the beam. The beam is as it is. In our hand is where we can apply this force P so that it cancels out this twisting moment that you're having, and essentially does not let the beam, along with bending, does not let it twist. Now if you see, this ff and ff times h causes a moment which is ff times h over here, right? So let's just quickly write this. So this guy over here, sorry, I should turn my pen on again. Yeah, so this guy over here and this guy over here separated by this h causes this particular moment. This is ff times h, right? So this is the moment, this guy over here, the moment that is happening, it is f times h, right? So this is the twisting moment over here. Now to cancel that moment, instead of applying P at the centroid, so to cancel this clockwise moment, I must have an anti-clockwise moment somewhere. I must sort of put my load P at a particular place where it causes an anti-clockwise moment equal in magnitude to this ff times h, so that the entire twisting moment is cancelled out. Now I am free to apply this load P anywhere about this horizontal axis. Here I have applied at the centroid. I can shift it to the right, I can shift it to the left, I can have some attachments to the beam, and I will come to the picture for that one. I can have some kind of attachments or some kind of configuration where I make the line of action of P, and as you can imagine, this P, instead of applying to the center, if I apply over here, so suppose if I'm applying the P over here, see this, if I apply a P here, so let me maybe hypothetically draw it. Suppose if I'm applying this P over here, right? This P, and see this P is always going to be there to balance out the externally applied load that is there. So if this P and this applied P over here causes an anti-clockwise moment which can help in resisting this clockwise moment over there. So let's go ahead and take a look. So the question is that can there be a location of P where as a result of applying that load P over there, there is not going to be any amount of twisting? And yes, the answer is true for that. So if for this one, if I apply a load P in that external beam over there, which is at a distance to the left of the section, where this P and this internal P over here, I can have a total moment. So I can have a P times E, which is the anti-clockwise moment. See, this is also the internal P that is developing over here. So let me just write that here as well. See, if I have this equal and opposite P separated by a E anti-clockwise moment, this should be sufficient to resist this clockwise moment. So if I just do this P times E and I choose the E, the distance E over here, such that equals to FF times H, then I'm completely nullifying the clockwise moment due to the FF times H over there, and I can resist the twisting of the beam. So this is the concept of shear center. So now you know what. So what is the shear center? Shear center is essentially this distance E. So shear center is the distance at which you should apply the load P such that the beam only bends and it does not twist. So force we applied at a distance E helps cancel the twisting moment over here, and this, my friends, is known as the shear center. So this particular distance that you see over here, this tells you where this particular point is, or where the shear center is, right? So let's take a look. So shear center is the point where the application of the load will not cause any twisting but just bending over here, right? So if you take a look, it is somewhat like this over here. You see, now instead of applying the load P at the center, I have somehow shifted it, right? Now how is it practically possible to do? Now see, in this example which I just showed you, previously the load was acting at the centroid. Now I have shifted the line of action of the load to the left of this channel section at a certain distance. So you see, this one is just now bending. It does not have any amount of twist. So let's compare it with the previous figure that we saw. See here, when the load was acting at the centroid, you were having bending and some kind of twisting over here, clockwise twisting. Now what I have done is that I have applied the load at a certain distance P to the left, such that you are having only bending and no amount of twisting over here. So this E gives you, this is exactly the formulation that we wrote over here, that is P times E. So this is again the P, the internal shear that is developing, that is V equals to P. So P times E is FF times A. So E gives you the location of the shear center in this particular case. So I hope this overall concept was clear. So what we are going to do is that we are now going to look at a problem example where we are going to take a similar channel section, a similar kind of a section like this over here, and for that we are going to compute the location of the shear center that is there. So let's go ahead and take a look at a problem example. This is the problem example on locating a shear center. So let's go ahead and take a look at the problem first. Try to understand what it is before going and punching in the numbers and finding the shear center. So what you are shown is a cantilever channel section similar to what we saw in the lecture, where at the end you are applying a load of 10 kilonewton, a vertically applying load of 10 kilonewton. Now as a result of this, we have seen that internally you develop these kinds of forces that are there, which results in bending as well as twisting. So it results in the twisting. Now you're supposed to find the shear center, that is essentially where you have to apply the load P. Now we have seen we have to apply the load P somewhere over here to find the shear center E. Remember, E is the distance at which you're applying the load P such that your element or your beam just bends and no twisting happens. Now some of the properties are given for this one. You are given the properties of the channel section, the height and the width and so on. This is an enlarged view of this section over here. So it has a width of 100. This is the centroid where your load is acting over here, and the thickness is 4 mm thickness. So it is a thin walled section that you have over here. Now from this you can easily calculate this area moment of inertia, which I have not calculated separately, but this is a given for this problem, so you can utilize this one over here. Okay, so now for this let's go ahead and first find that where the shear center of your particular beam is going to be. Now remember one thing is that these are the forces which are acting in the flange, and this is the force which is acting in the web, which is equals to the applied force P over here. So the first thing to find is these forces which are acting over here. So if you recall that these forces are designated by F of F, right, where this F of F times this vertical height H was equals to P times E to derive the shear center, right? So we have to find this F of F, right? Now to find this F of F, remember the precursor to that is to find the shear stresses. Now we know the shear stresses here is going to be a linear variation because it is perpendicular to the direction of the shear. The shear is acting vertically up at that internal section. So it is going to be so it is going to have a linear variation over here. It is going to have a parabolic variation and a linear variation over here, right? And the overall direction of the shear flow or the shear stress is going to be what? It is going to be somewhat like this over here. So we are going to have smaller arrows over here, to bigger arrows, to big arrows, then maybe a bigger arrow over here, and so on. So something like this is going to be your overall direction of your shear flow. So let's go ahead and first calculate Q, because Q is related to tau. That will give us the shear stress which is acting over there. So for this I'm going to take a small chunk. You can either start with a small chunk over here. Usually what I like to do is that from where the shear flow is moving away, I like to take a small chunk over there. You can either take a chunk here or take a chunk over here. The only difference it is going to do, you may think it is going to do, is in calculation of that capital Q, because Q, small q equals to V times capital Q divided by I. But either way, you have to consider for that capital Q, that area that you get A prime times Y bar prime, it is only whatever makes your calculation convenient. So I'm going to start by taking maybe a small chunk over here. So let me take a small chunk. So this is the chunk which I'm going to consider, and let's say this guy is at a distance S from here. Say this distance is S, which I have marked. So what I'm trying to find is that at this location, at this S, what is this value of Q which I'm getting over here. So let's go ahead and write that formulation for the Q. So we know that our Q, so this is at the flange I'm calculating. So at flange, so let me go ahead and write that. So at flange, because remember, so this part, this is the flange, the top and the bottom are the flange, and this guy is the web. So at the flange, at this part where I have taken this guy over here, this section, so here I am writing my small q is V times capital Q divided by I over here, right? So now V I know is 10 kilonewton, which is given in the problem. This is the shear force acting. I is also given in this one. So the question is to calculate the Q over here, as we always do. So now for Q, remember Q is A prime times Y bar prime. So here for this small chunk over here, the A is going to be S times this thickness. Remember the thickness all throughout is 4 mm. So Q is going to be your S times 4. So that is my A prime times Y bar prime. That is the distance of the centroid from the neutral axis. So that is 75 mm times 75. So if we plug all of these guys over here, you get the expression for Q as Q equals to 10, that is the load, times 10 cube. So I'm converting to Newton, times what we just calculated for capital Q, S times 4. So that will overall give you, I have this calculated already, it gives you 0.533 S. So it is in terms of S, because you see, oops, sorry, I wrote that behind my camera, so I will just write it below. That gives you 0.533 S. So it is in terms of S because you have this guy S over here. Okay, so now from here we can tell that at s equals to 0, so essentially at this edge over here, the shear flow q is going to be 0, and it is going to be maximum at this point d over here with a linearly increasing trend from 0 to here. So let's just write that. So at e I have my q, so this is the q at the flange I'm calculating, so I will mark it as qf. At e qf equals to 0, so at D, I get it as 53.3 Newton per mm. So this is the Q. I'm trying to calculate. From the Q, I'm trying to calculate the stress. So my tau of F is going to be, remember the relationship, Q is equals to tau times T. So tau equals to Q divided by T. That is 13.33 Newton per mm square. Why mm square? Because I divided with another unit of length over here. So here I'm going to have a linear variation. I'm going to draw the figure later. So I know I'm going from 0 to here to a linear variation over here. Right? Now next is, so here at the point D, now when I'm coming to the web, at the point D, whatever was in the flange, just like the flow of water, at the point D I'm going to have a horizontal jutting out portion here as well, which is going to be your 13.33. So my next point of interest is C prime over here, and I know from D to C prime the variation is going to be parabolic. So let me calculate the point estimate at C prime before drawing the figure. So as I said that in the web, so let's just write at web, we get, you know, q of web at D will be equal to q of flange at D. That was what we had calculated, that is 53.33 Newton per meter mm. So correspondingly your taus are also going to be same. So I'm going to calculate now at C prime. So to calculate at C prime now, I have to, so I'm essentially trying to find this arrow which is going to happen just leaving C prime. So I have to consider this entire area which is over here, so which is this guy, this area. So for this, I'm going to quickly write the value of Q. I can divide this entire into, write the value of capital Q, I mean. I can divide this entire area into this one chunk of rectangle, another chunk of rectangle. For this rectangle, I can calculate the A prime times Y bar prime, and for this rectangle, I can calculate the A prime times the Y bar prime over. So I'm going to quickly write it. You can go back and check whether it is correct or not. So what I just wrote over here, this bit is for this bottom rectangle, so A prime times Y bar prime, and the next bit is for this rectangle over here. So if I plug all of these guys back over here, let's see what is the value of QW that I get. I get the value of QW as 73.33. So correspondingly, I'm going to get my tau W. This is going to be simply divided by the thickness. So now that I have found what are the values of taus which are going to see, my final objective is to find this, you know, force in the flange which is over there. But now since I have found all, and I actually need not have found this one to calculate the shear center, but simply just for demonstration I've calculated everything. Let me go ahead and draw the distribution of the shear stresses across all the faces. So what I have just drawn over here is the distribution of the shear stress that is there. So the shear stress in the flange varies from 0 to 13.33 over here, and from 0 to 13.33. So you just like the flow of water, this ordinate must be equals to this one because there is no extra water coming from anywhere. So this must also be 13.33, and at the center at C prime, what we calculated 18.33, this is over here, and from here to here is parabolic variation, and the rest is just a mirror image at the bottom over here. Right? So now our job is to remember, our job still remains in calculating what is this FF over here, right? So that FF can simply be calculated by this shear stress distribution. Now remember again, I'm pointing this out over and over. This is just the representation of the magnitude, not the direction. So there is no direction. The direction is along this one over here. So if this is a tau f, which is varying from 0 to having a linear increase over here, how do we calculate the overall force, which is ff, which is acting over here? So the overall ff which is acting, we can write it as, right, so it is half times 13.33 times b times t. Now you have to try and understand this. So here you see, if suppose if this tau was a constant force, it was not a constant stress, it was not a linearly varying stress. Suppose it was a a constant stress. So how will you calculate the total force? How do we get the force from the stress? It is the stress multiplied by the area, right? So here the area is this area, so that area is your this width b, which is 100 mm, times this thickness t, which is 4 mm over here. But here your tau f is a linearly varying force. It starts from 0 over here, so it goes up to 13.33. So that is why you have this half of 13. It's like the triangular load, kind of a concept over there, right? It is half times 13.33, but the area over which it is acting, it remains the same. It is b times t. So if you plug in the numbers, let's see what we get. So we get 2666 Newton. So now we know to calculate the shear center, we have our formula, that is P times E equals to F times H. Now remember, we are trying to find the E. What is E? E is the, let me just mark over here, maybe E is this distance where I am supposed to apply this load P to resist the twisting which is happening over there. So let's go ahead and plug in the numbers and calculate E. The value of E that you get is 40 mm. So that is the location of the shear center that you have. So essentially, to resist the twisting of of this whole channel section, you need to apply this force P at a distance of 40 mm from this particular edge or from the center line, since it is a very thin section. So this is the E which we just calculated. This is, right? So to resist the bending, you must apply this load P. I will just hypothetically draw this one over here, which acts at this distance E from the edge. So that is how we located the shear center. So I hope this problem example was clear to you on how we calculate the shear center for a channel section. So you can also try out for other kinds of sections, which we'll take a look while solving some of the problems.